For 400 million people globally, a rare disease diagnosis is a grueling odyssey, averaging nearly 5 years and over 7 doctors. The clinical answers usually exist, but they are trapped in disconnected hospital data silos. Centralizing health records in data lakes creates massive privacy risks and legal friction. Traditional federated learning isn't the answer either. It's designed to find population averages, erasing the exact needle in a haystack and matches required for disease diagnostics. Project Aethelgard shifts from traditional models to Federated Retrieval Augmented Generation, or FedRAG. Effectively, we are creating a distributed search engine. Instead of moving sensitive patient data to the cloud, we move the computation to the edge. Here is how it works. Search queries are converted into vectors and mixed with empirical noise, making it impossible to reverse engineer the data. These protected vectors are sent to our superlink message queue. To maintain absolute security, hospital nodes use a pure pool architecture. They simply ask the queue if they have mail, requiring 0 inbound firewall configurations. The local MedGemma models act as a semantic firewall, summarizing the raw medical record into a safe, synthetic insight before sending it back. Alright, time for a live demo. As we speak, I'm spinning up the hospital nodes in the console. For this demonstration, we are running the superlink, the message queue, and the nodes all right here on this single machine. We've loaded our system with synthetic admission notes based on the real-world ChaseBIRT X-ray dataset. Here in our Clinician app, let's select a local patient profile, add a custom clinical prompt, and kick off the search. Perfect! While that runs, let's look under the hood. The app just converted our patient's file into a 1920-dimensional vector and heavily obfuscated it with empirical noise. Over here on the server console, we can see how the secure vector is broadcasted. Down here, the hospital node picks up its mail, finds the closest clinical match, and uses a local MedGemma for B model to generate an answer. We deliberately optimized our pipeline to minimize token usage so this can run on incredibly cheap hardware. In fact, everything you are seeing today is running locally on a standard laptop, even without a GPU. Okay, the answer is generated and uploaded. Let's check the application. And there it is. We receive a highly relevant clinical insight, completely stripped of any personally identifiable data. This gives doctors the exact historical context they need to select the correct treatment path, without ever exposing a patient's identity. We no longer have to choose between protecting patient data and finding a cure. The answers to rare diseases are already out there. And now, we finally have the infrastructure to safely connect them.